The first method we are going to study that uses neural networks is named Variational AutoEncoders and is based on variational inference. Let us recall the framework in which we work. We observe the variables x1 until xn, and we do not observe the latent variables z1 until zn, which are distributed according to a prior we specify pz. The complete likelihood is the one involving the variables z, assuming the variables z are observed, but we only have access to the observed likelihood which does not involve the variable z. In this framework, we can have different aims as finding the posterior distribution p theta z given x, the distribution p theta x, and generating new data. Note that here we have specified that all likelihoods depend on the parameter theta, so we are in a parametric estimation framework. A first question would be how to choose the latent distribution. If we are dealing with images, we could say that latent variables are descriptors for these images as angles, widths, colors, shapes, texture, and so on. However, these latent descriptors are specific to images, and we do not want to create manually all latent variables. Thus, it is difficult to create latent variables with specific meanings. Instead, we would like to create a generic latent variable without specifically looking at descriptors for images. It is also difficult to model dependencies between each component of Z. Since latent variables have no clear interpretation, we can draw these variables from a classic distribution, typically a Gaussian distribution, with the identity as the covariance matrix. In this way, there are no dependencies between the latent variables and they are easier to generate. In short, you see that the distribution you choose for the latent variable is quite simple. All components are independent and the marginals are distributed as a classical distribution. There is a key argument to choose a Gaussian distribution. Any distribution in d dimensions can be generated by applying a function to a normally distributed vector u of dimension d. So any distribution can be created based on a normally distributed vector. Can you prove it? You can pause the video. Assume that we want to model the distribution of x which has the following density f. You can decompose the density as a product of conditional densities. Now, consider the vector z distributed as a Gaussian vector of mean 0 and of covariance matrix identity. Let f1 be the cumulative distribution function of x1 and phi be the cumulative distribution function of a standard normal random variable. Then you know that f1 applied to x1 follows a uniform distribution on the interval 0, 1, and this is the same for phi of z1. Since the cumulative distribution function of a standard normal random variable is invertible, and if you assume that f1, the cumulative distribution function of x1, is also invertible, then you obtain that x1 follows the distribution given by equation 85. Now, we can denote by f2 x1 the cumulative distribution function of x2 given x1 equal small x1. Then we can apply exactly the same reasoning as before, and we end up with x2 being distributed as stated in equation 86. Repeating the same process allows us to generate a d-dimensional vector x following the pre-specified distribution where all components are functions of the vector z, which is normally distributed. If you want to know more about this statement and how to generate random variables, you can look at the paper below.